This meeting is being recorded.
For this next video, we'll take a look at what are referred to as zero-order reactions here. And notice that the rate of disappearance of A is going to be independent of the concentration of A in a zero-order reaction. So what that's saying is it doesn't matter how much you start with, the rate is independent of that, or it's completely a separate occurrence. So we see here for a zeroth order reaction, we have this integrated rate law shown over here. So what this tells us is that the concentration of A at time t is related to the initial concentration shown over here, A sub 0, and then we add that to the rate constant times time here, so the negative kt. So let's take a look at a problem where we can utilize this equation to solve for a zeroth order decomposition, where A again is our analyte, and this reaction is occurring at 300 Kelvin. Again, the K value is temperature dependent, so that's given right here. And we know that this reaction has an initial concentration of 1.9 molar, and we want to know at what time will the concentration reach this value here. So we can set up our equation for A sub t equals negative K times T plus the initial concentration of A here. So the values that we would plug in for A sub t, we know that we want to know the time at which we're 0.55 molar. So since we're given this K value over here of 1.5 molar per second, we're going to multiply that by T for time, and then we're going to add 1.9 over here. So what happens is to get the time in T here by itself, we're going to subtract 1.9 from both sides. So now our new equation will be negative 1.35, right? If we subtract 1.9 over here. So negative 1.35 equals negative 1.5 times T. So if I want to isolate my variable t, I'll divide both sides by negative 1.5. So that gets t by itself, and then negative 1.35 divided by negative 1.5. We're going to end up with a time of 0.90 seconds. And I know that's going to be in seconds because my rate constant was in molar per second. So that's an example of a zeroth order reaction and how we can utilize the integrated rate law to find a time once something reaches a certain concentration, or we can also solve for any of those variables if we have the others, including the K. So the next concept that we take a look at here is referred to as half-life, and we can define this as the time required, right? So time required for half of the reactant to react. So for half of a reactant to react, and you can look at that as half still remains. Right, so this is our half-life definition, and we know that relating this such here that the concentration of A at the T1 half will be half the initial concentration. So we can use this relationship here to help us out. And if we were to derive this half life equation, it would look like this, where we would have the natural log of 2 over whatever the rate constant K is, and we could define this as the half-life. So this equation here will come in handy, and notice that for a first order process, like this rate law is shown up here, or this half-life equation is shown here, it does not depend on the initial concentration. So let's look at sample exercise 9 here. And this reaction over here is graphed where we have our initial concentration up top here. And then we have varying rates of change of concentration over time. So we're going to look at this, remind ourselves this is a first order reaction, and see if we can use this figure, this graph, to estimate the half-life. So if our reaction goes down to 0 concentration, we want to know how long does it take to reach half, right, from this value here. So what's the half-life? So we're looking at this value here. So if we go across our graph and then we go down here, we could approximate at least 340, 350 seconds, something like that, until we reach our half of our starting concentration. So our half-life is somewhere in that range. Again, we're estimating. So now let's use the same information and see if we can calculate our half-life using that approximate value for t. So we know that t to the 1/2 is the natural log of 2 over k, and we want to solve for the rate constant here. So we want to solve for our k value. So we're going to rearrange this equation. So I'll multiply both sides by k, divide by t to the 1/2. So I know that my k will equal the natural log of 2 divided by 345 seconds or so. So when we do this, we get 0.693, and when we divide by our value in seconds, we get a k value approximately 2 to the -3rd per second.